going to be the last one in this semester, and probably we will set the key for this semesters. And my name is Xiaopen Li, and I'm associate professor at USF with the Department of Civil and Environmental Engineering. I'm co-hosting this webinar with Dr. Yu Zhang. She's also in the audience, and so she's waving to us. And so first of all, I want to thank all the audience for taking your time and dialing in. And I would like to ask you to mute yourself during the presentation, but you can unmute while you're asking questions and interacting with us. We're going to record this session, so if you have objections, please let me know. This event is actually sponsored by UTCs at USF and also the ITE student chapter. In particular, today's presentation is featured by the sponsorship of NYSER because it's very much relevant to congestion. And so, I'm the director of NYSER, so it's my great honor to introduce today's speaker, Dr. Michael Cassidy, and we're very fortunate to have him here. He's the Robert Horangeff Professor and Chancellor's Professor of Civil and Environmental Engineer at the UC Berkeley, and he's also an associate director for our UTC NYSER. You can look into the announcement to get some samples of the great achievements he have done. But I just say a few words based on my perceptions. Actually, I think first of all, I think he's a very well-known and renowned scholar in this field. And actually, one of my first papers that I read after I became a graduate student was multiple of his papers I read among the first batch, and they really inspired my research, and really, particularly I was very impressed and inspired by his way of using parsimonious methods to describe complex problems. Also, his students are everywhere in academia and other places, and I think my work is also quite inspired by his students at various universities, and even my advisor was supervised by Dr. Cassidy. I think also another thing I want to mention is, I actually was lucky to listen to his presentations right after I became a graduate student. So I was very impressed by his presentation. I still had some memories about his days to visit UIUC. That was a place where he gave us the presentation while I was a graduate student. So today we're very fortunate to have him to give us a presentation on the topic of impactful approaches to transportation system management. This also leads a collaboration between our group and his group on NYSER research projects, and I believe it's a good manifestation of his parsimonious way of describing a complex word. Without further ado, I would like to have Dr. Cassidy.
Well, Sean, thank you very much. I have to say you are way too kind, but it's very kind of you to say these things. But I also have to admit, now you've made me kind of nervous, because now I think I have to do a really good job, but we'll do our best here. So let me start by saying it's really a pleasure to be here and to speak. I really appreciate the invitation. And maybe I'll start by saying that when I was preparing this presentation, I started thinking back to the days when I first entered graduate school, which, yeah, as Shaw alludes to, was quite a few years ago. And I was reminiscing in this way because, as best I can recall, The first term that I was introduced to as a graduate student was the term Transportation Systems Management, or we'll call it TSM today for short. And of course, what we're talking about here are strategies that seek to get the most performance out of the transportation facilities that we already have. And what I remember most as a graduate student with regard to transportation systems planning is that a professor of transportation planning told me that TSM shouldn't really stand for Transportation Systems Management. Instead, it should stand for Too Small to Matter. And I suspect that the professor was arguing that bolder approaches are needed for solving urban transport problems. Now, these bolder approaches might include things like densifying land use patterns or shortening commute distances or perhaps other means. But I think mostly the professor was concerned with figuring out ways of giving greater competitive advantage to public transit. So I suppose in the professor's view, TSM was not really pushing the big, bold ideas that were needed to get the job done. It was thinking too small. And in the decades, the many years since I was a graduate student, it's still true that bold ideas are needed to solve urban transport problems, including especially ideas to enhance public transit. But it's also true, for better or for worse, that many urban trips are made by private automobile. So some attention needs to go there as well. And to this end, I see indications that some things maybe have changed in regard to TSM. And with these changes, perhaps TSM is no longer about thinking small and being too small to matter. I say this in part because recently I looked at the Federal Highway Administration's website and I discovered that the term has been expanded. Now it's called Transportation Systems Management and Operations. And as I looked a little further at the website, I got some clues that the expanded terminology may reflect an expanded and bigger way of thinking about what TSM really ought to try to achieve. So, for example, the Federal Highways website on the subject now offers an expanded list of the sorts of strategies that fall into the category of TSM. And here's a few examples that I pulled from that list. You'll note that the strategies mostly reflect supply-side measures that can add capacity to a street network. And you'll notice, for example, that the list contains the prohibition of disruptive left turn maneuvers at intersections. This is a rather old idea, and I'll offer evidence today that when deployed on its own, turn prohibitions may really be too small to matter. On the other hand, another carryover from the past is traffic signal coordination. Yeah, that too is an old idea. But today I'm going to offer ideas on how traffic signals might be coordinated over an entire city, and in this way be quite impactful. And then to me, what was most surprising is that the Fed's list of TSM strategies now includes demand-side measures, like congestion pricing, which can be very impactful, by the way, as we'll discuss today. I also find it interesting, or maybe I should say telling, that the Federal Highways TSM website advocates deploying TSM in what it calls integrated fashion. Specifically, the website advocates coordinating TSM strategies across multiple jurisdictions and across multiple travel modes. It also advocates deploying these strategies over entire transport systems rather than just at isolated locations. Now, this all seems like very good advice to me, and I think perhaps it reflects bigger thinking on the subject. So, in the second half of my presentation today, I want to discuss a different sort of integrated use of TSM. I want to show that TSM can be impactful and not too small to matter if we apply two distinct forms of TSM to a street network in joint fashion. Because we recently found that even if you apply the two forms to a single city or neighborhood, and even if these two forms are applied to serve only a single travel mode, still synergies can occur. In other words, you can achieve the favorable impacts of one TSM strategy, plus the full impacts of the other strategy, plus additional favorable impacts thanks to the synergistic interactions between the two TSM strategies. So then the whole becomes bigger than the sum of its parts. Now, before jumping into that discussion, I note one last feature of the Federal Highway's TSM website. It argues that advances in technology can and should be leveraged to develop TSM solutions to address congestion issues. Well, I certainly agree that technology can help in the execution of TSM measures, but technology alone cannot tell the engineer or the planner the sort of TSM measures that ought to be deployed for a particular city. I think answers to those sort of questions necessarily rely on the engineer's or the planner's creativity. And so what I'll mention about this is that our efforts at Berkeley to devise creative solutions to transport problems, well, in doing this, we've often found it helpful to first tailor solutions to simplified, idealized settings. We try to be kind of parsimonious, as Shaw suggests. And then if we find that our solutions hold promise and are not too small to matter for simplified cases, then we might think about how the solutions might be extended or adapted to accommodate the more complex conditions that can occur in real-world settings. And what I want to do, I want to illustrate this stepwise approach at the start of my presentation today. And I want to do that by discussing some ongoing research pertaining to the coordination of traffic signals across an entire city. So to sum up today's agenda, I want to discuss not one, but two research efforts at Berkeley that we are carrying out collaboratively with the colleagues who you see here. And as I said, the first effort pertains to coordinating traffic signals citywide. And the second effort, which I will speak on much more briefly than the first, it involves the joint deployment of two other TSM strategies. Those other strategies being first, the prohibition of left turns at all intersections on the network, and second, congestion pricing. Now, though these two research efforts that I want to talk about today are indeed distinct, they do share a common theme. I mean, both entail TSM strategies for enhancing urban travel by car, and perhaps more importantly, both offer evidence that if one thinks big, TSM strategies can have sizable impacts and not be too small to matter. I'll also mention that the two efforts that I'm going to talk about today are similar in that both have been supported by the NICER Center, which we very much appreciate. And I should also say that both efforts are ongoing. We haven't completely finished either effort yet, but still we hope that our findings to date will prove interesting and worth sharing. So let's discuss our first topic on citywide traffic signal coordination. As we do, we'll keep in mind that coordinating traffic signals entails synchronizing offsets. And we're going to define an offset as the start of a movement's green at an intersection relative to a master clock. Now, the goal, of course, is to reduce travel costs, which we're going to express in terms of vehicle hours traveled on the network and in terms of network-wide vehicle delay. So I'll start here by saying that when intersections are free of residual queues, meaning that queues dissipate by the end of each green, offsets are typically synchronized to the forward motion of vehicle platoons. But when residual queues instead form at intersections and grow long, well, in these cases, synchronizing offsets to the backward moving waves that propagate through those queues can be an effective response. In these latter cases, green times are not initiated until the intersection is cleared of any queues immediately downstream. Okay? This enables the movement to proceed through the intersection unimpeded during the green. Now, when dealing with one-dimensional networks, meaning signalized intersections that may serve two opposing travel directions, it's well known that when link lengths vary, then the offsets that work well for one travel direction may not suit the other direction. In these cases, folks have advocated selecting the offsets to favor the higher flow direction, since this can increase trip completion rates on the arterial and thus reduce delay. Now, this is a very good idea for resolving incompatibilities, and we're going to return to this idea shortly because incompatibilities can be harder to resolve on two-dimensional networks like grids. And that's because each intersection in these cases might serve 4 distinct travel directions. So now you have the possibility of incompatibilities occurring in all 4 directions. And what I'd like to say about this is that coordination strategies previously proposed in response to this challenge, they tend to be rather complex. So for example, they might entail the use of statistical methods or iterative techniques or AI-based approaches and the like. But in all cases, the methods proposed in the past seek to coordinate streets independently, meaning one at a time. But that's not really going to get us very far because, for example, one could optimize offsets for each east-west street in a network and then maybe get good coordination for those streets. But once you have the optimized offsets for east-west streets, you won't likely have good synchronization for the perpendicular north-south streets. So what we have here are incompatibilities in trying to synchronize offsets for orthogonal movements. Though this is true, it's also true, though, that past methods invariably have produced some improvements. What we see in the literature, for example, is that simulation is typically used to test a proposed strategy, usually against some commercially available computerized model, like the Synchro model, for example. Now, I'll just mention in passing that what Synchro does is it optimizes offsets by altering them incrementally and one street at a time until it finds a minimum cost in terms of network performance. And from the literature, we get the sense that maybe Synchro is thought of as the gold standard in benchmarking. So what we see invariably is that the proposed strategy du jour, in other words, the strategies that's being tested, invariably tends to outperform the commercially available method like Synchro, but never by very much, usually by less than about 5%. And the bigger problem with these previously proposed coordination strategies, and by the way, it's also a problem with Synchro, is that these strategies always assume steady state traffic conditions. But these are uncharacteristic of the situations of interest. What we're really interested in is oversaturated rush periods when queues temporarily spill over from one intersection to the next. So with that as background, what I'll say is that the strategy we've developed for coordinating signals on grid networks seems to be rather surprisingly impactful and not too small to matter. In part, this is because our strategy is dynamic to suit non-steady state rush period conditions, meaning with our approach, offsets are synchronized to the forward motion of free flow vehicles when intersections are undersaturated, and those offsets are synchronized to backward waves when links become filled with queues. Now let me mention that for both cases, we might envision a green phase being triggered by the arrival of a moving observer to an intersection. In one case, the observer is moving forward with a free flow vehicle or in a free flow vehicle. And in the other case, the observer is traveling backwards while riding a wave. But importantly, the offsets are chosen in our strategy to favor vehicle movements that are headed toward cluster destinations in the morning rush and away from those cluster destinations in the evening. And I'd like you to notice that this idea is akin to favoring the heavy flow direction on an arterial. And I want to stress that this idea can be applied to mono or multicentric cities. Maybe I should also point out that our approach requires that destinations be spatially clustered in some sense, though the destinations do not have to be densely clustered. But I would say that with our approach, it won't work all that well if, for example, destinations were uniformly distributed over an entire city. All right. Importantly, what I want to say here is that incompatibilities that might otherwise occur between orthogonal movements, like, for example, westbound and southbound movements, these can be resolved with simple systematic rules. And what our discovery is, and this is a discovery that we sort of kind of just stumbled onto, and what it is that we found that the systematic rules for resolving incompatibilities become surprisingly simple when we deal with idealized networks that form rectangular grids like the grid you see here. Now, we can say that this network is translationally symmetric, meaning all north-south streets along any single tier of the network share a common link length and a common vehicle free flow speed and a common backward wave speed. And we have the same sort of symmetry for all east-west streets along any one column of the network. Now, in these idealized cases, we find that we can always synchronize the traffic signals on a grid to any speed in two orthogonal directions, like again, the westbound and southbound directions. Okay, so let me try now to flesh out this idea using the simplest network possible. I'm going to use this small 2x2 grid you're looking at. Now this grid is rectangular or rotationally symmetric, and we realize that with this symmetry, one can synchronize offsets such that in undersaturated traffic, a vehicle like this blue one could travel along path 1, and then a vehicle like this red one could follow along path 2, and importantly, both vehicles could do so without being stopped by a red phase at the intermediate intersection along their respective paths. And we realized that we could expand this approach to a translationally symmetric grid of any size, like this slightly larger 3x3 grid that you're looking at. Again, a vehicle could proceed along its path without stopping at a red, except at the first intersection it encounters after having performed a turn maneuver. Most vehicles will have to stop at that intersection, but keep in mind that on a grid of two-way streets, a vehicle can travel between any two intersections and have to make at most one turn maneuver. And I also want to add that this stop requirement that we're talking about only arises when we're synchronizing offsets to the forward motion of vehicles. It doesn't occur when we're synchronizing signals to backward waves in oversaturated conditions. But before I say more about backward synchronization, first things first, let's ask the question, how exactly would we synchronize offsets for forward travel in undersaturated traffic? Well, I'm going to keep things simple for our discussion, and we're going to assume that streets on this network are homogeneous in that they all have the same fundamental diagram for describing traffic. And we'll say that all intersections are controlled by pre-timed two-phase traffic signals with a common cycle length and equal green times for both phases. So let's try to introduce these ideas for a morning rush in a monocentric city where, in this particular case, we're going to say that the trip destinations have a center of gravity in the network's lower left corner, meaning those destinations reside near the intersection that we've labeled intersection 5. Now, since we're talking about traffic that is undersaturated, we'll select the intersection further away from that cluster, meaning we're going to select intersection 1 at the upper right corner of the network, and we're going to say that intersection 1 is our reference intersection. Now, its offsets are the times when its east-west and north-south green phases start relative to a master clock that resides at that intersection. We can call those offsets delta ref. And I'd like you to notice that the superscript I here distinguishes the east-west signal phases from the north-south phase. Now, you might ask, what about all the other signals that reside on the network? We might call another intersection intersection J. Well, using VF as the vehicle free flow speed and XJ and YJ as the east-west and north-south distances between the reference intersection and intersection J, then the offset for any intersection J is given as shown, where C here is simply the signal's cycle length. Now, the same ideas apply when queues spill over from one street link to the next, and offsets are synchronized to the backward waves that propagate through those queues. The distinctions we make in this case are rather minor. For one, the reference intersection is no longer the one residing furthest from the cluster destinations. Now what we do is we move the reference intersection to be the one that resides closest to the destinations. So in our example, keep in mind there's going to be intersection number 5. And offsets for this new reference intersection are again set relative to a master clock. And The offsets for any other intersection J on the network are now going to be determined much as before, but are now based on the trip time for an observer traveling backward along a wave from the new reference intersection to an intersection J. Okay. Once again, this synchronization can be achieved for any two orthogonal directions, and this will be true for all networks, including very large networks, as long as they have the kind of symmetry we've seen in our examples. And that's fine because many networks, many real-world networks, have these symmetries, at least approximately. But at this point, we should ask, well, what about networks that are not symmetric? Well, here's an example that's similar to our earlier 2x2 network, except now this small grid is not translationally symmetric. And that's because the vertical link on the right-hand side of the network is curvy. All we're trying to say here is that trip time from, say, intersection 1 to intersection 4 is going to be longer if one travels via path 2. Now, because of this, we cannot synchronize all the signals in two orthogonal directions, but there is something that we can do. We have seen that networks with certain symmetries can be near perfectly synchronized. So the game now is as follows. When we have an asymmetric network, like this small one we're looking at, we find first the symmetric version that most closely resembles our asymmetric network. And we find this symmetric version by averaging link characteristics along tiers and along columns if needed. We then select offsets for the symmetric version, and we use those offsets for the actual asymmetric network. It turns out that this approach can work pretty well, meaning we can easily adapt our method to suit the kinds of non-idealized asymmetric grids that can occur in the real world. But before I demonstrate this, there's just one more quick technical detail I want to mention. You will recall that our dynamic strategy toggles between forward and backward synchronization as grids transition between under and oversaturated conditions. Now, I just want to say that if this toggling were to occur without any intervention, then signal phases can be unreasonably short at the transition between forward and backward synchronization, like the phases I've labeled here with Roman numerals. So, to make a long story short, we've coded a few simple rules to prevent this from occurring, and we integrated the algorithms into our strategy, and we find that following a transition time now between forward and backward synchronization, our algorithms ensure that all streets on the network will be fully coordinated within 2 cycle lengths. So finally now, we've tested our idea using simulation. We simulated traffic on 20 by 20 signalized grids, starting with this translationally symmetric rectangular one. The details of each intersection are shown on this pop-up. And I should say we used time-varying demands that would create congestion on the network. And in the morning rush, here's a kind of a key detail. We first assumed that destinations are clustered in the center of the 20 by 20 network. We distributed the destinations as a joint normal in such a way that 40% of the destinations reside in that shaded 6 by 6 subnetwork you see in the center of the larger grid. Now, because the destinations were so dense in this centered 6 by 6 network, its links became oversaturated during simulated rush periods. So as a result, or in response, within the 6 by 6 subnetwork, our strategy toggled between forward and backward synchronization as conditions changed inside that subnetwork. Now, for drawing comparisons, let's consider a morning rush. And let's start with a case in which all signals on the 20 by 20 network have 0 offsets. And what that means is that the green times for north-south movements initiate all at once across all intersections on the network, and the same is true for the east-west phases. Maybe I should mention that this kind of signal coordination is often done for dense grids like in Manhattan, and maybe we can think of this case as our baseline. So then, this is, very importantly, a time series of vehicle accumulation, meaning the numbers of vehicles on the 20 by 20 network for the baseline case with 0 offsets. And the important thing to note here is that the area under this curve is the total vehicle hours traveled, or the VHT, on the network. So this area under the network is something we want to reduce. Well, towards that end, here's a time series of network accumulations when offsets were optimized by the Synchro program. So the shaded area between the curves is the savings in network VHT achieved by Synchro. Synchro reduced VHT by 5% relative to the baseline, zero offset case, and the savings in delay was around 7%. So we can say that Synchro did some good, but it didn't do much good. I say this because here's the accumulation curve when the grid's offsets were synchronized using our approach. Now the differences are quite dramatic. Our approach reduced VHT by 25% relative to what Synchro achieved. And the savings in network-wide delay, again, over and above what Synchro could do, was more than 30%. So it seems our strategy worked pretty well. And I should mention that we found that our strategy works quite well in other settings too. So for example, we simulated various levels of urban sprawl in monocentric cities, and we looked at a multicentric city, and we examined the afternoon or the evening commute when folks were headed home from work. Now, for various reasons, our strategy turned out to work even better in these other settings. Very importantly, we tested our strategy on a 20 by 20 network that was not translationally symmetric, but where east-west streets were inclined at angles of about 1.5 degrees. We synchronized offsets based on averages taken over tiers and columns of the network, and to make a long story short, we've already seen that the Synchro program is not all that impactful. So what we did in this case is we tested outcomes from our approach against what we can call a greatly enhanced version of Synchro. We created Synchro to optimize offsets all at once across the network instead of one street at a time. And for good measure, we gave this enhanced Synchro the added advantage of deciding that all of its vehicles would have onboard technologies, and these technologies would allow cars to speed up whenever necessary to catch green lights. But even though our method did not enjoy the benefits of these vehicle technologies, our method still outperformed the enhanced version of Synchro. What we're seeing here really is kind of a testament to the benefits of being dynamic, of toggling between forward and backward synchronization. So I think the point is our method seems quite good. And I want to stress again that we stumbled into these ideas by starting from simple idealized conditions. And I say this because idealizations also proved helpful in another ongoing project that we're pursuing with nicer support. Very briefly, I'd only want to take a few short minutes to talk about this second project, if you'll indulge me just a few minutes. Because in this second effort, we've looked at an idealized version of the street network in downtown Los Angeles, and we found that TSM strategies can be more impactful if we deploy two strategies at a time. Now, that in itself is not very surprising. What is surprising is that we found that synergies can occur in this way when the network is sufficiently congested. So then, one of the TSM strategies that we considered was a demand-side measure. Namely, we looked at a congestion pricing scheme that levied tolls based on the vehicles miles traveled in the network. Now, the strategy that we looked at imposes relatively low monetary tolls by instead incentivizing longer distance commuters to travel either earlier or in later portions of a rush. So, and then commuters incur on punctuality costs for arriving either early or late to work, just as in that seminal work by Vickery. I should mention maybe in passing that penalties for early or late workplace arrivals were expressed in units of in-vehicle travel time, so that we could describe how commuters trade on punctuality for time. And I'll just mention that the earliness and lateness penalties we used were those we found in the literature. But at the same time, we also considered a supply-side strategy, one that could add capacity to the network. And the supply-side strategy we looked at was simply the prohibition of left turn maneuvers at all intersections on the network. What we did is we examined morning commutes where fixed numbers of commuters chose when to depart their homes to go to work, so as to minimize the combination of in-vehicle delay due to congestion, as well as any toll they might have encountered, which we expressed in equivalent units of time, plus that on-punctuality penalty for arriving early or late to work. Now, what you see is the network of major streets in downtown Los Angeles, which we idealized as a 20 by 20 rectangular grid with trip origins and destinations that were uniformly distributed over the network. Now, our analyses, I should mention, relied on network-wide relations between vehicle accumulations and average speeds, and, not surprisingly, these relations were affected by supply-side changes, meaning in our case, the relations were affected depending whether or not we prohibited left turn maneuvers. And I'll just mention that we generated these relations through simulation. Now, all these inputs were simulated with an agent-based model, and the simulations were performed in iterative fashion to emulate equilibriums that might occur over many days. And we performed these simulations for a number of scenarios. First, we had a baseline do-nothing case where we did not implement any TSM measures on the network, on the LA network. We also looked at what would happen to traffic on the network if all we did was to prohibit left turn maneuvers at intersections. And then we looked at what would happen to traffic on the network if we deployed all by itself our VMT-based tolling scheme. And then finally, and rather importantly, we looked at what would happen on the network if we deployed both TSM measures together at once. And part of our analysis was to vary demand, meaning the number of car trips parametrically. So the curves that I'm going to show you now display the percent savings in the combined travel costs relative to the baseline do-nothing strategy. And the gray curve that you're looking at, it shows the percent savings for the left turn prohibitions when that was the only thing we did on the network. Now you'll notice that this gray curve drops below zero, meaning that the turn prohibition saved costs, but not much costs. It seems to me that maybe banning left turns and doing nothing else might be too small to matter. But on the other hand, this green curve is the curve for congestion pricing when it was the only thing we did on the network. And you'll notice that this demand side strategy is much more impactful in terms of saving costs relative to the baseline. And then importantly, this third curve in red, it sums the cost savings of the two measures when each measure is deployed on its own. Yeah. Now, at first glance, we might think that this red curve is the lower bound on cost, meaning we might think it's the best that we can do because after all, when you deploy two TSM strategies together, the benefits of one might overlap or even partially cancel out the other. But that's not what actually happened, much to the contrary. This blue curve you're looking at is the simulated cost savings from the joint deployment of both strategies together on the network. And surprisingly, this blue curve consistently falls below the red curve, which we might have thought would have been the optimistic prediction of joint effects. And the blue curve falls below the red curve whenever demands are greater than about 40,000 car trips, which, by the way, is the approximate lower bound where congestion occurs on our network. So the main point I want to make here is that the vertical displacements between the red and the blue curves quantifies the synergistic effects. Those displacements quantify the extents to which the whole exceeds the sum of its parts. Now, you'll notice that the synergies are greatest for a demand of around 70,000 car trips, which coincidentally is comparable to what our estimates of downtown LA's morning demand is. And in this case, we see that nearly 30% of the percent cost savings comes from the synergies. And what we can say is that it turns out that the two strategies, when deployed together, tended to increase vehicle speeds and congestion. But at the same time, I should point out that that both TSM strategies have some impacts that are unfavorable. For example, we know that turn prohibitions add to a network's vehicle miles traveled, although not by much in our example. On the other hand, the negative impacts of congestion pricing were more pronounced. I mean, that's not surprising. I mean, some pricing strategies, for example, they levy rather stiff tolls. And then there's a problem of having a transfer of wealth because these tolls are taken from commuters and they usually go somewhere else. You know, the tolls go somewhere else. Now, in our case, the strategy that we used actually kept monetary tolls fairly low, but what it did is it imposed rather sizable unpunctuality penalties where people arrived early or late for work. And whether we're talking about high tolls or being tardy for work, these are the kinds of things that can engender public opposition to congestion pricing. And that might be unfortunate because, as we saw in our simulations, pricing can be a very effective means of combating congestion. So our simple thinking is just like this. We say, well, if joint deployments of multiple TSM strategies can achieve synergies, then an already effective strategy, like congestion pricing in our case, can be made even more impactful. And that extra favorable impact might help in diffusing public opposition to a strategy like pricing. And if cities are not stymied by public opposition and can therefore deploy congestion pricing, well, then cities might make some real headway in terms of ameliorating their congestion problems. So finally, in conclusion, first of all, thank you so much for listening to me, but my closing thoughts are this. As I think back again to the time when I was a graduate student, I appreciate that bold actions are still very much needed to remedy urban transport problems. And some of those actions can entail radical changes to land use policies and radical changes to commute patterns. And certainly we need to do a better job of promoting public transit to collectively transport people in large numbers. But in concert with this, with these fundamental changes in city forms and travel behavior, TSM strategies can be impactful as well. But what's required is that we think big on how to use these strategies. And we really need to design and deploy these strategies in thoughtful and targeted ways. So that concludes everything I wanted to talk about today. Thank you very much for your attention. I'd be very happy to try and answer questions or to discuss anything you might find you want to discuss.
Thank you, Dr. Cassidy. What a nice and insightful presentation. Any questions from the audience? You can unmute yourself and directly ask the questions.
I have one question. Why in the slide that you showed the joint development, the joint,
the joint deployment of two strategies,
the joint deployment of both strategies and the combined ones, given that in the first, less than 20,000 vehicle demands, you could see that the joint development was not performing as well.
Right.
Well as the other alternative. I wanted to ask why that was.
Well, yeah. So we're still kind of wrestling with the mechanics of the synergies. What we do know, and we have some thoughts, but they're kind of incomplete. What we do know is that the synergies had the advantage of increasing vehicle speeds in queues. But when traffic is not queued, there's a simple lesson here. Don't employ strategies. Don't tinker with what isn't broken. You can do damage. So that isn't a very theoretical answer, but it's kind of a practical observation.
Thank you so much.
Yeah.
One other thing is that with prohibition of left turns, since we're looking at potentially increasing travel distance.
Yeah.
Does that increase fuel consumption dramatically across the network?
Well, there's kind of a trade-off because you travel more miles, but you spend less, you increase capacity, so you spend less time idling in queue. You spend less time traveling on the network. So there's a kind of counterbalancing effect there. Now, where things come down in terms of fuel consumption and emissions and so forth, that's going to be kind of case specific. But it's not all bad news. I mean, if you're going to do, say, left turn prohibitions in concert with something more impactful, and I think you should probably do it with something more impactful, not just on its own. There is a concern. There is a concern with the extra distances traveled. But it's also true that they'll spend less time traveling, and that has good things for the environment as well as the economy. You guys, you want to speak? Ibrahim, you want to chime in? Ibrahim did most of the work for this thing joint TSM deployment. Maybe he has some thoughts on the matter.
Yes, hi. The increase in VMT was around 16%. That's the increase in distance due to the left turns, but the VHT went down significantly, especially delay. There is a significant reduction in delay, and once people's travel break less, they might spend less fuel, especially in congested conditions.
Thank you.
Thanks for the questions.
Great, thank you. Any other questions?
Hi, Dr. Cassidy.
Hi.
I have one question. This is Said, a PhD candidate from USF.
Nice to meet you.
Same here. Thank you for the great presentation. I was curious about one thing. So I can see that you used a fixed time signal plan for each individual, signalized intersections. So I was wondering, when you are, finding the offset, did you also consider, the phase sequences, considering, changing the phase sequence to sort of make it easier to find the best offset, along a grid?
Yeah, so I commend you on your astute observation. We've looked at very simple cases with regard to signalization at this point. We've got pre-timed signals. All green times are the same for a north-south street across all intersections and for an east-west.
Right.
Now, that said, there are things that can be done to introduce more complicated signal timing plans.
Right.
There's ways of, for example, and I think this could be important, you could implement at some intersections protected left turn phases, for example, where you'd need to, but you just take that away from the through movements on the green. But I think there are, in the end, and we're probably not going to go very far in this direction, or maybe we will, I don't know. But in the end, there's probably a lot of things you could do to tinker with this idea in terms of changing signal plans and getting more complex multi-phase signals. But I think you're going to run up again. I mean, I think there's going to be a limit too to what you can do. You have to have a certain kind of symmetry across the network. And if you get too far from that, this thing may not work very well. I don't know. We'll have to wait and see.
Right. The reason I'm asking is I found that you started with a simple network, but in one of the examples that you had also directions. I was thinking, of course, if you have only two phases, then the phase sequence doesn't mean anything.
Right.
But I thought that the examples that you have right now, the preliminary examples, have more than two phases. So that's why I was.
No, I'm afraid all we've got now is two phase.
All right. Thank you.
Basil, you want to add something?
I think like you answered pretty accurately. I just want to say that I think it is possible to apply it when you have more than just two phases, but the constraint is that the different phases should have the same duration. I mean, phases across different intersections should have the same duration.
Yeah, so there are there are going to be some limitations here to maintain the symmetry.
Thank you.
Yeah, thank you.
Yeah, I'd like to mention, actually, we met once, Dr. Cassidy, with Saeed, and he's the person
yes.
transit.
Yes, of course.
Project.
Nice to see you again. Although I can't really see you.
Yeah, and I think one way to look at this is that I like the approach to start from the homogeneous approach, and then we can add on some adaptations to further improve the results based on the more detailed settings, and we could use some numerical methods. That's what Saeed is doing, and so I think there will be also some interesting potential for theoretical findings if we not necessarily these signal like time phase durations are identical, but if they have certain multiplication relationships or multiples, something that there could be something to do, and it has some interesting mathematical properties maybe.
Yeah, you're absolutely right. Of course. I mean, as a simple example, we could do the thing they call double cycling, right? At some intersections. That would be easy, but that's just one example. But I agree with everything you said. Yeah.
Yeah. So I encourage Sid. You can talk to Ibrahim and Basil and to like to learn what they're doing, and we can sort of as a way to further collaborate down the road.
Sure. Yeah, this is a great opportunity. I really enjoyed today's presentation.
That's very kind of you. Thanks.
Other questions?
Oh, hi, Mike.
Hi, you. How you doing? I see you actually.
I think Sharpen didn't overstate when he was introducing you. I really enjoyed presentation.
Well, I'm afraid you're both wrong on that one, but we'll have to agree to disagree.
Remind me about listening to lectures at UC Berkeley. So I just ask if you could elaborate a little bit on the demand management, the strategy, because we know that the demand management so far was not so successful in the US. And also there are some tools that have been developed by researchers for providing credits to encourage people to change their departure times. Yep. So in your study, when you talk about demand, can you please elaborate a little bit on that?
Yeah, what we've used a strategy by DeGonzo and what I'm blanking out on the guy from Illinois. What's his name?
Are you talking about Nicholas?
Leahy.
Leahy.
Sorry, sorry, I forgot Leahy. What they did, they've developed a VMT-based strategy that will enable most commuters to escape with very low tolls, but because it's VMT-based, and of course the tolling changes with time of day, longer distance commuters are going to be more inclined to travel in the very early or the very late portions of the rush. So the real penalty with this particular strategy, which makes it a little different than a lot of other strategies, is that you don't have much of a toll you pay, but a lot of people are really early or really late for work. And that's a penalty. You know, there's no free lunch. I suppose I agree with you that most efforts at pricing in many parts of the world haven't been terribly successful, but that doesn't mean that they cannot be. I think if you use the right kind of strategy, and maybe you double down with another strategy to go along with it, I think you can get some success. I mean, London claims success. Their strategy is rather clumsy, but it gets the job done to a certain degree. And I think you could do even better if you were careful about how you set things up. But I mean, that's what we're academia, so we get to sit in the ivory towers and say, oh, well, it should be simple to do. And I have no doubt when you try to deploy it in a real city with all its complications, it's going to be difficult. But I think and I don't know if this is really answering your questions, but this is the thing that's coming to my mind, is I think if you start with this idealized, parsimonious way of thinking about it, and then you try to keep to that to the full extent you can, and you depart from it only when you have to, I think there may be opportunities for being impactful in the real world. I think it's worth a try.
If I may chime in here, with the VMT-based strategy, as Mike said, the unpunctuality costs being earlier or later than you want increase. But to make it more acceptable to the public, when we apply it with jointly with the term prohibitions, these earliness and lateness, these additional earliness and lateness penalties drop by around 40%. So it makes it much more acceptable to the public and easier to apply.
Yeah, that's a good point. Thanks for bringing that up, Ibrahim. Yeah, the synergy kind of makes both strategies better.
Yes, that's great. Yeah. Thank you.
Thank you.
Yeah, great. Any questions? Any further
Well,
questions?
again, thanks. I really enjoyed that. We really enjoyed this. Thank you very much for having us.
Well, thank you. So I guess, all right. Yeah, and I really enjoyed this presentation. Look, so I feel like one takeaway I have is sometimes when we look into a complex problem, we always think from a complex way. But if we but I think it's more important to make complex problems simple and make big problems small at the beginning too. Otherwise, we would miss the opportunities of improvement. For example, if you notice the results between the comparison between Synchron and this parsimonious approach on that simple network, we could have missed that 20 or 30% of the benefit potential if we just start with complex, with a complex problem, without taking advantage of the insights and the parsimonious structure of the system. So yeah, and I also like to say, maybe this also inspired me to think about other strategies of improving transportation systems. We had a question about how to make it impactful. So I think it's the challenge to the reality is that it feels like the stakeholders would all often like to take an incremental approach that doesn't change dramatically of the current system. We could think about how to bridge this with the current practice. Just to try to find a pathway to guide them there with incremental changes. For example, prohibiting the left turn would create some like an additional miles traveled. Maybe we could think of having some reimbursement or I don't know, credit or from this whole system.
Yeah.
Instead of tolling to make them a little bit as more incentive, I think some of the researchers in Hong Kong proposed like tradable credit or something.
Right.
that these are also directions to think about. So with this, I want to again thank Dr. Cassidy as well as the UC Berkeley group very much for this nice presentation. I learned a lot, and I hope particular fellow students, you can. I have to mention that the way to organize slides and making the presentations to be are very helpful for you to make final presentations. I know many of you are going to make final presentations. This is a good experience, and I think this is the last one. That last seminar we have for the Friday transportation seminar series, which makes me a little bit sentimental at this point. But we're gonna resume this seminar series in the fall semester. And in addition, NICER has follow-up seminars hosted on a separate platform, but during the summer we have a number of great speakers as well. Please check them out at the NICER website, nicer.usf.edu. And with this, I want to thank all of you again. Hope you have a good weekend, and also best wishes to our students for their finals.
Yeah, thank you, Dr. Cassidy, for your presentation. I just wanted to mention that the USF IT chapter lecture